Good afternoon. My name is Tom Sawinski, and I work for the Department of Energy's Office of Advanced Reactor Technologies. I'm here today to present an exciting opportunity in the NEAP Mission Supporting RC-1 work scope pertaining to innovative and transformative research for advanced reactor concepts. Before I go deeper into work scope details, I'd like to first provide to you an overview of the objectives of the Office of Nuclear Energy, followed by a description of our programmatic areas, and then provide you an overview of the current advanced reactor research and development taking place. The Office of Nuclear Energy as a whole has several key objectives. First is develop technologies to improve reliability and sustain the safety and extend the life of our current reactor fleet. Secondly, we also want to develop improvements in the affordability of new reactors to enable nuclear energy to meet our future energy goals. We also aim to develop sustainable nuclear fuel cycles and also to develop capabilities to reduce the risks of proliferation and terrorism. The Office of Nuclear Reactor Technologies, also known as NE7, attempts to accomplish these goals through its mission, which is to keep the current fleet operating safely and to develop new concepts and technologies for future deployment. To do this, we focus our efforts on promoting technologies that have great promise to enable new nuclear. We conduct research and development to maintain safe operation of our current fleet. We work to honor our commitments with federal agencies, international partners, and also universities. We look to maintain unique capabilities and facilities to support future industry needs. And I want to point out this last bullet here, we would like to explore new high-risk, high-reward technologies, which is a large premise for this particular mission-supporting item. NE7 is broken into 3 offices. NE7-2, which is the Light Water Reactor Technologies Office, NE74, which is the basis of our Advanced Reactor Technologies Research and Development, and NE75. The remainder of this presentation will primarily be focused on NE74 research and development. As I stated previously, the research activities are designed to address technical, cost, and security issues with various advanced reactor concepts. This graphic right here simply provides graphical representation of the breakdown of NE7. I'd like to point your attention to the middle of the screen under the Advanced Reactor Technologies group. Within that, we have 5 subcategories that we perform our research and development on. They are fast reactor technologies, high temperature reactor technologies, generic technologies for advanced reactors, licensing framework, and system studies. This slide provides a brief overview of each of the 5 categories and what the mission is for each particular category. For fast reactor technologies, we're focused on actinide management, electricity production, and have a primary focus on sodium coolants. For high temperature reactor technologies, we look at both electricity and process heat production, and we focus primarily on gas and liquid salt-cooled systems. Advanced reactor generic technologies looks at common needs for all advanced reactor types, such as materials, energy conversion, decay heat removal systems, and modeling methods. The regulatory framework field looks at licensing requirements for advanced reactors, and reactor system studies looks at capital costs, operations, and fuel costs for advanced reactor types. Now, all these fields in the Advanced Reactor Technologies program looks to address several key questions. They are, how can we improve the affordability of nuclear power? Can we improve on inherent safety of advanced reactors? How do we improve the proliferation resistance of advanced reactors? How do we address nuclear fuel waste issues through advanced fuel cycles? How can we expand into non-traditional nuclear energy markets? And also, how can we increase the performance and efficiency of these reactors while also making them cost competitive? Currently, we have research going to address these questions, and right now I'm going to focus primarily on the reactor side of the Office of Advanced Reactor Technologies Research and Development. The first field is Advanced Fast Reactor Technologies, which is broken into several subcategories, which are concept development, technology maturation, advanced materials, advanced energy conversion, safety and risk reduction, and ultrasonic viewing technology. For concept development, we're continually looking for assessments to guide innovative R&D into the future. Currently, we are looking to conduct small-scale sodium fast reactor components testing at the Materials Engineering Testing Lab at the Argonne National Lab, which is currently under construction. In terms of advanced materials, we have down-selected 2 candidate alloys, and intermediate-term testing is currently taking place on these alloys. In terms of advanced energy conversion, we're utilizing a sodium to supercritical CO2 interaction loop at Oregon National Lab to monitor the interactions between these two media. In terms of safety and risk reduction, we're looking at licensing aspects and reducing capital costs for these reactor types. And also, for in-service inspection, we are focusing research on ultrasonic viewing technologies. In the high temperature reactor field, we have two categories. The first is high temperature gas reactors. Three main fields that we are focusing on are fuel qualification, passive decay heat removal, and materials. In terms of fuel qualification, we are working to establish a licensing basis for coated fuel particles known as TRISO, and also for the commercial fabrication capabilities. Testing has been performed at very high temperatures so far with no failures, making the technology very promising. In terms of passive decay heat removal, we're working with the Natural Convection Shutdown Heat Removal Test Facility, or NSTF, at Argonne to evaluate ex-vessel passive decay heat, and also the High Temperature Test Facility, which will be up and running at Oregon State, will be used to verify and validate fluids modeling programs in terms of decay heat removal. And like for the fast technologies, we are also focusing on materials, including high temperature materials, and especially graphite materials for high temperature reactors. The second high temperature reactor that we currently have research and development underway is fluoride high temperature reactors. This is primarily funded through the Integrated Research Project, one which was awarded in 2011, and proposals were currently solicited in 2014. We also utilize international collaborations with China on their test reactor activities in this field, and also with the Czech Republic working on the use of salt in that particular reactor type. Now that we've gained a general overview of the research and development ongoing, I'd like to go into the details of this particular work scope, which allows us to look outside the box at innovative and the next generation of reactors outside of what's currently being studied in the Advanced Reactor Technologies program. As it shows, we are looking for revolutionary improvements to advanced reactors, or even in potentially new concepts in advanced reactor realms that improve reactor performance and safety. This can be done in a multitude of levels, which I have here, such as incorporating advanced system components into existing concepts, including innovative design alternatives such as new fuel types, nano-engineered coolants, looking for designs employing radically different technology regimes, such as advanced coolants, operational regimes, and also looking for reactors that provide unique capabilities outside of base load production, such as mobile reactors or process heat. This slide provides a more condensed summary of both the research and development ongoing and what we're looking for in this particular scope. So as I've stated, a variety of reactor technologies are currently being pursued in our portfolio, such as high-temperature gas-cooled and sodium-cooled reactors and liquid salt reactors. Other technologies were also reviewed by the technical review panel at the links shown. Now the MS-RC-1 scope looks for major innovations to advance reactor concepts currently underway, not necessarily building on ones that are already available. That is under the RC2 scope. So we're looking for advanced systems, either with advanced current types, or, as the second bullet shows, we're looking for radically different technology options, which can be new reactor types or innovative operating regimes, and also reactors with unique capabilities other than base load electric production. And like the graphic shows, the object of this particular mission supporting item is to think outside the box and allow you to give comments and recommendations for the future of advanced reactor research. This provides some awards that we've given over the years, and it shows the broad spectrum of items that this particular scope looks at. So in FY13, you see there's a multitude of items such as tritium mitigation and control systems for fluoride high-temperature reactors. On FY12, stationary liquid fuel fast reactor concepts for transuranic waste burning. FY11, safety assessments for advanced reactors using vented fuel. So as you can see, from different operating regimes to entirely different reactor types, this particular work scope provides the opportunity to really think outside of the box. And with that, I now open it up to any questions you may have.
Over the next few minutes, we'll be taking any questions that you may have for Tom. We also have Bob Hill on the line to answer any technical questions that you may have. What is the proposed range of core coolant outlet temperature in sodium fast reactors?
For this particular scope, there is no designated range of the outlet reactors. If you're looking for more of a technical answer, Bob Hill would probably be the best to answer that particular question.
Yeah, current reactor concepts are in the 500 to 550 degree C outlet range. There are some concepts that look at higher temperatures, but most of the designs to date are in that range.